Okay. So, this is the BPSK simulation script that we had before. Hopefully, you remember this, how we were doing running uh, the uncoded thing, how we were using this randi command to generate messages, etc., etc. Okay. So, now let us see how to modify this for getting the coding implemented. So, I am going to save this as something else. So, I will say BPSK rep3 sim. Okay. So, this is the coded case with the repetition code. So, the first thing is we can keep maybe the EB over N naught at some more reasonable value 5 or something, that does not matter. First thing is the rate. The rate is going to be 1 by 3. So, like I said, N equals 3 repetition code. So, this is 3 symbols for 1 bit. Okay. So, 1 by 3 bits per symbol. Okay. So, after you fix your rate, the rest of the calculation is not too bad. Your EB over N naught is 10 power dB to regular value conversion, and then you find the sigma corresponding to the EB over N naught. Okay. And then so this is not quite correct. So, there is no need for a theoretical thing. So, we can delete that. Okay. So, now here we have to change things a little bit. Okay. So, you will this N will not really enter the picture. So, we can delete it off. So, you have blocks, each block is a code word block. Okay. Remember that each block is a code word block. Let us say we simulate 1000 code word blocks. So, what do we mean by code word blocks? In one block there will be one message bit, it will get encoded into 3 code word bits and that will get transmitted. Okay. So, now I will have to do block after block after block. Okay. So, it is useful to define a few things here. We can define k as the number of message bits. Okay. And we can define small n as the number of code word bits. Okay. So, this is good to have, and once you have this, so let us go ahead here. The message itself for every block, this loop goes for every block for I equals 1 to n blocks, and then for in every block I am going to generate a random bit. Okay. So, this will just be 1. So, since I need just k bits, I will put 1 comma k. Okay. Generate random message, random k bit message. Okay. Alright. So, now I have to put in my encoding. Okay. So, remember my encoding is just repetition code and I know my k is just 1. So, I just have a 1 bit message here. One can do a lot of things here. So, I will do a very simple encoding MSG, MSG, MSG. Okay. So, this is N equals 3 repetition code. Okay. Is that all right? So, now so encoding is complete. So, maybe I will put down a little bit of a gap here. Okay. So, then you have the symbol vector, it is 1 minus 2 into not message, but code word, right. BPSK is bit to symbol conversion for the code word, and then after that this is 1 comma n. Okay. AWGN channel goes here. Is that okay? So, hopefully you can see what I have done here. Nothing much has changed except that I have a k bit message in every block, and then I have a code word. This encoding operation can be more complicated depending on what code you pick. For the repetition code, it is just message, 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 there is no problem. Once you have the code word, everything is same as before. Okay. So, you do 1 minus 2 into C word. You remember how I did 1 minus 2 into if a code word bit is 0, I get plus 1. If the code word bit is 1, I get minus 1. Okay. And then you have the value of sigma. You multiply this with n Gaussian random variables. Why do I do n here? Because that is my code word, right. So, I have to generate n Gaussian values with the standard deviation of sigma. Okay. So, I do that, add it to the symbol vector s here. So, all these things become vectors. MATLAB is quite decent about handling these kind of things. So, you do not have to make much changes here. Okay. So, after you get the received value, you have to do decoding. Okay. So, you can do multiple types of decoding. So here I have done thresholding at 0. So, maybe one can do hard decision decoding here. Okay. So, remember hard decision decoding, you are still going to threshold at 0, but we call that vector as b, right, b. B is the vector which you did for thresholding at 0, and then I am going to basically see if B is either 0, 0, 0, 0, 0, 1, 0, 1, 0 or 1, 0, 0, if it has a fewer number of ones. So, let me show you the picture here. So, this is the lookup table I have to implement. Okay. So, there are various ways to implement the lookup table. I am going to basically count the number of ones in B. If it is 1 or 0, I will make the code word as 0, 0, 0. If it is 2 or 3, I will make the code word as 1, 1, 1. Okay. So, that is my strategy. So, let us do that. Okay. So, if sum of B, which is going to count the number of ones, is greater than 1, okay, then C word cap equals 1, 1, 1. Okay. So, actually, I mean, if you think about it, you do not need the message, the code word estimate. We can directly do the message estimate. We can simply say the message estimate is 1. Okay. So, this is better. You can try to find the code word, but really you are interested in the message, right. So, that is you do that, else you say message cap equals 0, and then you can end it. So, that is it. Okay. So, that is a simple hard decision decoder. So, how do you implement soft decision decoding? So, maybe I will call this as message cap 1 to indicate that this is hard decision decoding. Okay. The next one is soft decision decoding. Okay. So, in this case, if you remember, I have to do R1 plus R2 plus R3 and see if it is greater than 0. So, it is just simply sum of R, and if it is greater than 0, I will set message cap 2, or maybe I will put that as less than 0. So, to have it similar to before, equals 1, else message cap equal to 0. That is it. Okay. So, these kind of decoders for the repetition code are very easy to implement. Hopefully, you agree with me that it is the same. So, I have done a hard thresholding here. This is the threshold at 0. We spoke about how to do thresholding. You can simply set R less than 0. If it is negative, it will become 1. If it is positive, it will be 0, right. So, that is how it is. And I am counting the number of ones here. Okay. If the number of ones here is greater than 1, okay, then I set my message cap as 1, 2 or 3, that is. Okay. So, and here if on the other hand, if the number of ones in B is 1 or 0, my message cap 1 is going to go to 0. Okay. Now, you have soft decision decoding, which is message cap 2 here, 1 or 0. Is that okay? So, here a number of errors, you have to either pick 1 or 2. So, maybe I will pick 1 here just to get the hard decision decoder working. And then after that, you have to make a bit of an adjustment here. The BER simulation will actually be n errors divided by k by n blocks. Okay. So, for every block you have one message bit here. There is no BER TH, and we can simply plot this. Okay. So, this is how many bits, how many message bits were transmitted, how many errors happened, and what BER you got in simulation. Okay. I am going to run this, but let us maybe increase the number of blocks to 10,000. Okay. And my EB over N naught, maybe I will keep it as 4. Okay. So, let us run this. So, the name of this file is bpsk rep3 sim. So, let me go to the command window. I do not think I am in the right directory. Okay. So, okay. So, let us run this. So, we need to do format short g. So, there you go. Okay. So, it gives you an error of 0.03. There were 300 errors, which if you remember, it is a good statistic. 300 errors not too bad, and we ran 10,000 blocks. So, let us compare and see if this is sort of expected in the plot. Okay. So, 4 dB EB over N naught, 1, 2, 3. So, this is 0.3 0.3. So, you can see 4 dB EB over N naught. This is the number that I expect, and that is 0.03. Okay. So, it is simulating correctly. Maybe one can do 6 dB as well. 6 dB I expect around 7 or 8 into 10 power minus 3. So, let us run that as well. So, to get that, I am going to change the EB over N naught to 6, okay, save it, and then come back to the command window and then run it again. Okay. So, you had 73 errors. Maybe this is not very reliable, maybe you can increase the number of blocks by 1 more, but the answer we got was what we expected, around 7 or 8 into 10 power minus 3. Let me show that to you once again. So, this was around roughly 7 into 10 power minus 3. Okay. So, we are getting the right curve. So, that is working out quite well. Let us do soft decision decoding for the same SNRs, same EB over N naught 4 and 6. Okay. So, I am going to do soft decision decoding. So, for that all I have to do is to change my message cap 1 to message cap 2. I am doing actually both, I am just not using one of them. So, let us go back to the command window, okay. And now remember I am at 6 dB EB over N naught, 6 dB EB over N naught and soft decision decoding. Doing this, and you can see the gains, right. So, there were only 21 errors. Maybe this is not very good in terms of reliability. So, maybe one can increase the number of blocks to say 100,000. Okay. So, this will also give you reasonably good answers. So, if you repeat this, so you are getting 100,000 blocks simulated, 2.46 into 10 power minus 3. So, one can check that this is the correct value as well. So, at 6 dB EB over N naught, this is around 2.5, right. So, this point is around roughly around 2.5 into 10 power minus 3. Okay. So, that is pretty good. So, what we got in simulation agrees with that, and you can see the gains at the same EB over N naught because you did better decoding, soft decision decoding, you had a gain of about a factor of 1/2, a little bit more. Okay. So, 2.5 into 10 power minus 3 was the answer we got. Okay. So, hopefully this little coding exercise was good in terms of showing you how to do error control codes. Let me quickly run through. The first thing is the rate. Okay, you have to modify that, and that changes your sigma calculation, and you have number of bits in each, number of message bits in each block, number of code word bits in each block, how many blocks you want to simulate, and inside that you have the same picture. You do encoding, you do the transmission. You could choose to do either hard decision decoding or soft decision decoding. Okay. This is how it works, and then there are these minor adjustments in calculating the number of errors and all that. Okay. So, that is repetition code for you. Okay. So far we saw the repetition code, we saw how to implement it, maybe a little bit of analysis, and then how to implement that in MATLAB as well, and we generated these curves and we plotted it, and we saw that at the end of the day we did not get coding gain in EB over N naught. That is because of the way the rate is normalizing the SNR. Okay. So, next code we are going to see is a very famous code, it is called Hamming code, and in that code we will get some coding gain. Okay. It's the first real code that we are going to see. So, let us go through that.